In this video, we're going to focus on properties of rational functions. Now, a rational function is simply a polynomial divided by a polynomial. As you can see here, we have 2 minus x over x plus 2, 3x squared over x squared minus 9. It could be one very basic, 1 over x, for example, would be considered a rational function. And in the first one here, we want to find the domain of each rational function. Now, the domain is simply the values of x for which the function is defined. Now, a rational function is defined for all real numbers except those that make the denominator 0. So all you have to look at is the denominator. So for the first one, we got f of x is equal to 2 minus x over x plus 2. What number makes the denominator 0? We can see it's negative 2. So this is going to be defined for all real numbers except negative 2. Because if you put a negative 2 in the denominator, negative 2 plus 2 is 0. That's division by 0. That's undefined. So that's the answer to the first one. Now for the second one, we have 3x squared over x squared minus 9. Let's factor this as difference of squares. So this is x minus 3 and x plus 3. So if I put a 3 there, I get 0. 0 times anything is 0. So a 3 in the denominator for x gives me 0. A negative 3 will also give me 0. Negative 3 plus 3 will give 0. 0 times anything is 0. Cannot divide by 0. So in this case, we have two restrictions for the x. It's a set of all x. X cannot be negative 3 or 3. So that's the answer for B. Now for C, we have x minus 1 over x squared plus 1. X squared plus 1, you plug any real number in there for x, you're never going to get 0. So for this one here, we'll simply say for C, I won't give a set notation here. We can just say all real numbers. If you're using interval notation and you write negative infinity to infinity this way, in parentheses on both sides, that would be the same thing. So the answer to part C, the domain is all real numbers, no restrictions, or negative infinity to infinity. Now for D, again, what numbers make the denominator 0? So just factor this out in this case. We get x minus 5 and x plus 1. The numbers that make the denominator 0 are going to be 5 and negative 1. So this one is defined for all values x except 5 and negative 5. So we'll put this 5 here and negative 1. So the domain is all x except 5 and negative 1. Now for the next one, we want to identify vertical asymptotes, horizontal asymptotes, and oblique asymptotes. And these are just lines that the graph approaches. And these are just lines that the graph approaches. The graph will never cross a vertical asymptote. Generally, it doesn't cross the horizontal, but in some situations it may. Same sort of thing for the oblique. So the way we find these is simply we look at the denominator. For the vertical asymptotes, we look at the values that make the denominator 0, but not the numerator. Because if it makes the numerator 0 also, then you've got to have a hole or a missing point on that particular graph. So you can see here that you put 3, you replace the x by 3, you get 3 minus 3 is 0. So that would be a vertical asymptote. And that would be a graph, again, vertical, that the graph approaches but doesn't touch. The horizontal asymptote, again, is a horizontal line that in general the graph approaches but doesn't touch in most cases. But there could be some cases where it does cross. And for that, you simply look at the degree. If the degree of the numerator is less than the degree of the denominator, up here it's 1, x to the first, they're the same there. But if on the numerator you just had a 1, in other words, the degree of the numerator was less than the degree of the denominator, then y equals 0 will always be a horizontal asymptote. If the degrees are the same, and they are here, 1, 1, you simply take the coefficient here and the coefficient here, divide them out. 4 divided by negative 1, negative 4. So x equals 3 and y equals negative 4 are the asymptotes. Now for this, the next one, B, vertical asymptotes here, we look at the denominator. What number or numbers makes the denominator 0 but not the numerator? But you can see that x squared minus 1 factors into x minus 1 and x plus 1. So the numbers that make the denominator 0 would be 1 and negative 1. As long as those numbers don't make the numerator 0, and they don't, so x equal 1 and x equal negative 1 are the vertical asymptotes. Now if the degree of the numerator is 1 larger, and it is here, degree of the numerator is 3, degree of the denominator is 2. If it's that situation, then you don't have a horizontal, but you have an oblique. That would be a slanted line that the graph approaches and in general doesn't touch, even though it may in some cases. In that case, what you do is you use long division. So you take 2x to the third plus 3x, and you divide by the denominator, which is x squared minus 1. X squared into 2x cubed will give me 2x. Then multiply here, that's 2x to the third. 2x times minus 1 is a minus 2x. And then we subtract here. These cancel out. 2x cubed minus 2x cubed canceled. 3x minus a minus 2 makes it a plus. So this is 5x. So this is equal then to the partial quotient here, which is 2x, plus the remainder 5x over x squared minus 1. So remember, the idea of a asymptote is what happens to the graph as x gets real large or x gets real small. Well, you can see that this denominator, as x gets large, this value here is going to get large. So you're going to have 5x over a very large number. This is going to go to 0. As x approaches infinity or plus infinity or minus infinity. So this goes to 0, you're left with 2x. That tells me that the graph approaches the line y equal 2x. So it's a slanted line. We call it a slant asymptote, or sometimes called an oblique asymptote. That's the solution to that one. Now for the next one here, we have f of x is equal to x to the fourth plus 1 over x squared minus 1. Now if the degree of the numerator is more than 1 larger than the denominator, and it is here, I got a 4 and a 2, there is no horizontal or oblique asymptote. If there's any values that make the denominator 0, and x squared minus 9 factors into x minus 3 and x plus 3, so the numbers that make the denominator 0 are going to be x equal to 3 and negative 3. There is no horizontal or oblique asymptote. Now for the next one, D, again in summary here, if the degree of the numerator is less than the degree of the denominator, and it is, this is a 1 here and this is a 2, the x-axis, which represents the horizontal line y equal to 0, is always a horizontal asymptote. No oblique. There are no numbers that make the denominator 0. X squared plus 1, no matter what you plug in there, as long as you plug in a real number, you're never going to get 0. So we only have a horizontal asymptote, which is y equal to 0. That's the x-axis. Now let's look at the last one here. Graph each function here, the rational functions. Let's just look at this part of the graph, y equal 1 over x. That's one of the basic graphs that looks like this. So we're going to use transformation techniques here. And you can verify that by just picking numbers. You pick x to be 1, we get 1, that point there. X to be 2, it's 1/2. X to be 3 is 1/3. So as you pick large numbers, the y value is decreasing. As you pick numbers close to 0, like say 1/2, 1 over 1/2, it goes to 2. Get close to 0 here, x is 1/10, plug it in there, we get 10. So the graph is approaching the y-axis. So this one has a vertical asymptote at x equals 0. Remember, I'm ignoring the minus 2 for now. And because the degree of the numerator is less than the degree of the denominator, it's 0 here, x to the 0, so it's 0 degree, and then 1. Horizontal asymptote would be y equal to 0. And you can check this graph here by just plugging in numbers here. -1 goes down here, -2, -3, and so on. So that's what the graph of f of x equal 1 over x minus 2 looks like. If I add the minus 2, it's this same graph here, except it moves it 2 units down. So instead of having a horizontal asymptote here, I'm going to have it 2 units down. This is going to look something like this now. So it's still gonna have a vertical asymptote at x equals 0, which of course is the y-axis, and the horizontal asymptote will be y equal. Instead of y equals 0, it'll be y equal to -2. And that's what the graph looks like. Now for this one here, just so it's clear here, I'm going to make this 2 over x. What if I look at 2 over x? Then I'm going to have a vertical. It's still a rational function, very basic one. Vertical asymptote is going to be at x equal to 0, just the y-axis. And a horizontal asymptote would be at y equal to 0, which is the x-axis, because that's the value that makes the denominator 0. So it's undefined there. And also because the degree of the numerator is less than the degree of the denominator. And then I'm going to put the square here. So notice, as x gets 0, notice x cannot be 0, so that's out of the picture here. But if I pick values for x equal to 1, 1 squared is 1, and then divided into 2 give me 2. So this goes up like this. But as the x gets larger, the y values get small, so this is coming down this way. It's approaching the x-axis. That's why we have a horizontal asymptote there, y equals 0. On the other side, you pick negative numbers, -1 squared. Again, it's going to be 2. And then as the x gets larger, because you're squaring it, it's going to approach the x-axis from like this. So it's going to go up like this and like that. So that's what the graph of y equal 2 over x squared looks like. Now, what happens if I make that a -2 here and then square it? Again, just like we did in the earlier video, that's a transformation. It's the same graph, except this moves over 2 units, like that, and 1 unit up. And instead of having a horizontal asymptote at y equal to 0, it's going to be y equal 1. So the line's going to pass like this. The vertical asymptote, instead of x equals 0, it's going to be x equal to 2. And then the graph is going to look like this. Approaches the line y equal 1, the horizontal asymptote, and approaches the vertical asymptote, which is x equal 2 now, shifted over 2 from both sides. Thanks for watching. We'll see you next time.